So today I'm going to begin a new topic. Okay. By the way, before I begin, let me just somebody last time asked me about Einstein-Rosen bridge, right? I didn't mention the name, but that geometry that connects two universes, right? That is what is called the Einstein-Rosen bridge. Right? We saw the black hole, the fully extended Schwarzschild geometry, right? Has two asymptotic regions connected in the interior, right? That's what is called Einstein-Rosen bridge. And then in quantum gravity, there are various speculations of that being related to EPR, PRs and so on. Okay, but that's not part of this course. Yes.
Is this still a manifold? It has a manifold.
Yes, indeed. This is a manifold with boundary, right? The singularity you can think of as the end as a boundary, right? Yeah. So it has the structure of a manifold. Because otherwise, it's perfectly smooth, right? Everywhere. Okay. So these are what are called geodesically incomplete manifolds, right? Because you can consider a geodesic which in finite proper time will end, right? Which hits the singularity. In principle, yes. I mean that's. Yeah, well, hopefully, I think we now know enough about the universe so that we are not inside, but indeed, there can be an event horizon inside an event horizon, right? Imagine that, I mean, some black hole has collapsed, right, and formed a event horizon, and then another big object could collapse, right, and form a bigger event horizon. Yeah. I mean, these are best captured in what is called the Penrose diagram, right, which basically captures the light cone structure, right, and you can capture those in this diagram. Okay, so today we are going to discuss action principle for gravity.
On top of that another layer which is collapsing. Also for a single thing that to be a single mass distribution, only one event. How is the
Well, you can imagine that there is a black hole, right, and then there is a shell outside, right, outside the black hole which is collapsing. Okay. So imagine that there is a small black hole here, right, with some mass m, okay, and then it's surrounded by another shell of mass m, right, which is collapsing. Okay. So as long as the radius of the shell is larger than 2 gm, okay, this is the only event horizon you have, right? Because this is a black hole and it has its own event horizon, right? Once you go in, you cannot come out. But once this radius becomes less than 2 gm, right, then anything from outside which crosses this 2 gm cannot go back, right? So it looks like there are two one-way membranes, right? From the outside observer's viewpoint, of course, this is the only event horizon, right? Because this is what limits the ability to come back. Okay? But suppose you are here, right? This is very large.
So it's something like the closest law, like when you have a closed surface only the inside charge matters.
Yes, indeed, that's right. Yeah, because that you can check, because again the derivation that we gave, right, really relies only on spherical symmetry, right, the action. So I mean, it really depends on the mass distribution. As long as it's a spherical mass distribution, right, you can think of it as if it's a point charge, as long as you're outside that mass distribution, and inside the mass distribution you don't have any effect. Well, it's a boundary in the sense that if you look at this extended diagram, right, we have this hyperbola, right? This has net dimension, which is 1 you see in the RT plane, and then the theta phi direction, right? So any geodesic, right, which once it enters the horizon, it has to end here. Right? So in that sense, it's a boundary, right? You cannot go beyond this. Right? So if you look at the whole geometry, right, this forms in the RT plane, at least this is like a boundary of the space time, right? Any other question? Yes, okay. It's basically this. Yeah, it's the fact that this universe and this universe are connected in the interior, even though you cannot travel from one to the other. Through the event horizon, yes. Yeah, so this basically is, well, I mean, you can say the whole geometry is a bridge, but as a spatial slide, this is like the bridge, okay? That you cannot cross from one side to the other. But if you want to meet, you can go inside and meet. That's right, yeah, exactly. Right, you can communicate, but you communicate inside. Okay, so let me remind you what the general action principle is. Yeah, the general action principle is that you have some variable, okay, whose equation of motion you are trying to derive, and you write you represent the equation of motion as a result of an extremization. Right? That's the general action principle. Like in particle mechanics, right? You write an action and then you vary the trajectory of the particle, and the action is extremized along the classical trajectory. Okay. So we want to see if we can do similar thing for gravity, right? And I'll explain what we mean by doing similar thing for gravity. Okay. But first, let's just start with particle mechanics. Okay, but a particle that is moving under gravitational field. Okay. So first, particle moving under background gravitational field. Okay, here you already know what the equation of motion is. U square. Where U is the affine parameter. And this equation we already saw that can be derived from an action principle by extremizing something. Right? That's the length of the curve. Right? So the corresponding action can be derived from the action. Okay, if you vary this, okay, take some arbitrary time-like trajectory and then vary by infinitesimal amount and demand that the first variation is 0, okay, then you get this condition. But what we will do now, okay, is to do a little more. We'll fix the normalization constant. Okay? And the claim is that the normalization constant here is to be chosen as minus m, okay, where m is the mass of the particle. Now it's clear that just by demanding that the variation of this gives you this, you cannot determine the normalization. right? Because the normalization is just the overall factor that will drop out of this anyway. But we have fixed it by some criteria, and that criteria, one of the criteria that you can use is that in the non-relativistic limit, it should give the correct result, right? That you are familiar with for a non-relativistic particle. Okay, and since it's just one constant that is to be determined, right? Once you determine it in any case, it's just the same constant. So let's try to verify that in the non-relativistic limit, it gives the action that you are familiar with. So first, let's take particle in flat space time. Let's consider particle. Let me call this Sx. Okay, which means G mu nu is eta mu nu. So then the Sx that we have written there can be written as minus m integral. If G mu nu is eta mu nu, then this is dx mu dx0 du square minus dx du square. Is it clear? Okay. So now we are going to convert this to the non-covariant form, right? Non-covariant but more economical form, where you will regard x1, x2, and x3 as function of time, rather than x1, x2, x3, and x0 as function of u. Okay? We just eliminate x0 by setting, so set x0 of u equal to t and eliminate u. Okay, this is the standard way of describing the particle trajectory, right? x1, x2, and x3 as a function of time. This one is more covariant way. Yes, indeed. You are minimizing a proper time. Well, they are just proportional to each other, right? So the same derivation, if we can go through, right, it works correctly. Okay, because it's just 1 minus square root of minus 1 taken out, right? So the derivation doesn't really change. The only thing you have to make sure is that you start with a time-like trajectory and vary infinitesimally, so that the deformed contour trajectory is also time-like. Right? You can't cross over between time-like and null, because then this becomes 0, right, on the way, and then this becomes ill-defined. Right? But as long as you start with a time-like trajectory and make an arbitrary variation, right, the same derivation will work that we use to get the geodesic equation. Okay, so if you do this, then Sx can be written as minus m integral du dx0 du. I'll just take this out, and then 1 minus dx dt square to the power half. Because dx du divided by dx0 du is dx dt, right? When we express this x in the as a function of time. And this is just dt. Okay, so this I write as minus m integral dt times 1 minus dx dt square to the power half. Okay, so far it is exact. We have not made any approximation. Okay, except that we have set the background metric to be flat. But now I'm going to make an approximation by assuming that dx dt is small, because that's the non-relativistic limit, right? Dx dt should be small, because we have set c equal to 1. If you remember that, so t here is really scaled by c. So in the non-relativistic limit, Yeah, if you are willing to use that, then you don't need to take it, right? But if you are not willing to use that information, then you take the flat space limit. Yeah, so if you have already seen, right, then you recognize that this is the Lagrangian of a relativistic point particle, right? So you don't really have to do anything more. Yeah, but I'll just take the flat space limit anyway, so that, because that is something probably everybody has seen, right, in classical, standard classical mechanics. So non-relativistic limit is dx dt small. And this becomes minus m integral dt times 1 minus half dx dt square plus higher order terms that we don't keep. Okay. So we see that we do have half m integral dt times dx dt square okay, that's the standard integral of the kinetic energy minus m integral dt okay, this term is not really relevant, this is a constant that you are adding to the action. But if you are willing to probe a little deeper, you can just think of this. You see, m is a rest mass of the particle, right? That is like a constant potential energy, right? So this is like integral t minus v, right? If you think of m as the potential energy of the particle. Normally, we don't include it because m is just a constant. Okay, but in the strict sense, right, you should have added that m or minus m in the Lagrangian. So this is the correct normalization. Right? That shows that this minus m that we have chosen is a correct normalization. Okay, or the minus m that we have taken here.
Calling m as a constant potential because it adds to the integral part. Why are you calling it?
It's integral t minus v, right? From that point of view, m is like a potential energy. But you can also think of the m, this is a rest mass energy, right? So it's certainly contributing to the energy, but it doesn't depend on the velocity of the particle, right? So it's more like a potential energy. Right? It is that there is a constant potential energy, so it has no relevance for classical dynamics. Right? But if you just think of this as integral t minus v, then this term is there. If you had sorry, I didn't get that.
Can we see a potential energy term there explicitly?
If you want to change that geodesic term, you want to change this equation.
Yeah, I mean, if we have some other force, let's say
oh, if you have, yeah, you are saying if you have say electromagnetic force.
Yeah.
Indeed, we'll study that, right? You need to add more term in the action, right? Does this term will not be good enough? Okay. But in principle, right, everything should be derivable from an action. Well, it's not guaranteed, but it's nice if you can derive it from the action, right? Because particularly in the quantum theory, right, when you apply for path integral formulation, having an action is very useful. Okay, so now we are going to do something else. Okay. We'll take the same action that we had written down there, okay. But this time vary the metric and see what we get. Okay. Take that action, assume that the particle trajectory is given, okay. And then you want to change g mu nu to g mu nu plus delta g mu nu, okay, and ask what is the variation, okay, and what will happen if you set it equal to 0. Okay, so extremize with respect to the metric. So vary g mu nu to g mu nu plus delta g mu nu. Then delta S becomes integral du minus m
Just a background.
No, now it's not a background anymore. You want to think of metric as a dynamical object. Right? Because ultimately, what you are interested in is to derive all the equations, right? So metric also you are allowed to fluctuate, right? Assume it's a very dynamical variable. Right? So it's like earlier in the first part of the course, we studied what happens when the particle moves in a metric. Right? But then we also studied how the particle affects the metric. Right? You want to study that kind of question here, right? So allow think of the metric also as a dynamical variable.
So we should also have gravity.
Well, so far we only know about this part, this action, right? So let's start with this and then see what we get, right? And then we'll worry about anything else. Okay, so in any situation, right, it's best to start with something that you know, right? And then you see if it gives something not sensible, you have to modify it, right? So right now we know that that action is there. So let's try to see what happens when you vary the metric in that action. Okay. So this we can calculate this by chain rule. So minus m integral du g mu nu. Let me write 0 sigma minus sign. Yeah, I forgot. There is a minus sign and there is a minus sign, right? Is this clear? Now we can choose u equal to tau. U is just a parameter, right? Okay, is this step clear? Right? We wanted to vary this, right? So delta of x to the half, right, is half x to the minus of delta x. Right? So that is half x to the minus of. Right? Maybe I can write the minus sign here, so there's a confusion. And these are delta x part. So if we choose u equal to tau, then minus 0 sigma dx rho d tau dx sigma d tau is just 1. Right? Because d tau square by definition is minus 0 sigma dx rho d sigma. That's a proper term. So this is just 1. So this becomes minus m integral d tau. This is 1. And then minus half delta g mu nu of x. So this one I'm going to write in somewhat more complicated fashion. I'll write this as, so this half minus half and minus m gives you half m. That part is straightforward. and I'm going to write integral d4x just multiplied and divided by the same thing. Okay, it's exactly what this is, because if you can do the integral d4x using the delta function, right, that will set small x equal to capital X of tau, right, which will make the argument of g mu nu as capital X of tau. Okay. These two cancel anyway, because that's basically this. Is this clear? Right, I have just rewritten a simple expression in a somewhat more complicated form, right? First by multiplying by and dividing by something, and then I introduced an integral, but that integral can be easily performed by using this delta function. The only thing that we have gained by this process is that the argument of delta g mu nu has become an independent variable x, small x, right? It's not tied to this capital X, right, which is a particle trajectory. Right? Of course, the delta function sets small x equal to capital X, right? But written in this way, right, the argument of delta g mu nu is just this variable small x that you are integrating over. Why it was something necessary to do? Yeah, next step will make it clear why this is something necessary to do. Well, it's not necessary, it's just, I mean, this is the way you can write it in a form that you recognize. So this quantity is integral d4x square root of minus determinant g of x delta g mu nu of x. Now, this is the T of the particle. This is the energy momentum tensor of particle. Okay, we have written down the expression for the energy momentum tensor of the particle, if you remember. That had a 1 over square root of minus determinant g of x. Okay, that's why I needed to multiply and divide. Okay. It also had this delta function, right, which said small x equal to capital X. Okay. And then these m dx mu d tau dx nu d tau were part of the definition of the energy momentum tensor. Okay, this half was not part of the definition, so that's why there's a half. Is it clear? So now you see that if we take that action and demand that its extrema with respect to g mu nu, or take an arbitrary variation delta g mu nu and require that the result should be 0 first order, then that will tell us that tx mu nu is 0. Okay, which is not a very sensible thing to do, right? I mean, no equation of motion is available that sets tx mu nu equal to 0. We know what the equations of motion are, right? The equation of motion for x, and equation of motion for the metric, etc. Right? And none of them instructs us to set tx mu nu equal to 0. Is that clear? So you cannot simply demand that you take that action, vary with respect to g mu nu, and set it to equal to 0, right? It gives you something that is not part of any equation of motion. But this does suggest something non-trivial, and that is that if you recall, T mu nu actually appears in an equation of motion, right? Einstein's equation has T mu nu, right? T mu nu equal to 0 is not Einstein's equation, right? But T mu nu does appear in the Einstein's equation, right? So if you could get the other part of the Einstein's equation from varying something else, right, then perhaps this will form part of that equation. So recall Einstein's equation. Okay, that was R mu nu. Let me write it on top because it appears there. Okay, and in this case we have only x, so T mu nu is just Tx mu nu. We can also write this as minus plus equal to 0. So what we should ask ourselves is it possible to get equation like this from a variational principle? And we see that we have already got part of this, right? The Tx mu nu we have got. Okay. So you have to somehow get this part. Is that clear? Okay. So let me write this in a somewhat more suggestive form. So I write this as 1 over 16 pi g times minus R mu nu plus half R g mu nu equal plus half T mu nu equal to 0. So I have done it, normalized it this way because we got half T mu nu there. Okay. So somehow you have to get this. Right? So what we need a new term in the action, S, which we can call S gravitational, such that delta S gravitational is given by integral delta G. Right, because then delta S gravitational plus delta Sx. Okay, if you add and demand that the coefficient of delta G mu nu is 0, then you would get the Einstein's equation. Yes. In this derivation, no, we have not used the geodesic equation. No. But the geodesic equation, of course, will come when you vary with respect to x. Right? But so far we haven't used. Is this point clear? Because you are trying to derive Einstein's equation, right? I mean, so what you saw first is that if you take that action, see, normally when you write an action, right, you don't have a choice that you will vary only with respect to some dynamical variable and set it equal to 0. You have to vary with respect to every dynamical variable that you have and set it equal to 0, right? Then you have the correct action principle. So we had part of the action, right? That action for x. By varying with respect to x, we got the equation of motion for x. Right? But G mu nu is also a part of the dynamical variable, and by varying with respect to G mu nu, we didn't get anything that is sensible. So now we are trying to get something that is sensible, right? And that is that we are trying to get by varying with respect to G mu nu the Einstein's equation, right? Because this part is already matching this, right? So what we need is to add something else so that we get this, right? And that something else should be independent of x, because if it involves x, capital X, right, then it will change the geodesic equation. Right? We don't want to change the geodesic equation, right? So we need something that is independent of capital X, but whose variation produces this. It should come out to be Einstein's equation, exactly, right? Because the general action principle is that you vary with respect to all the variables that you have at your disposal and set the Hodge variation to 0, and that should recover all the equations that you have in your theory.
When we vary, like when we suppose that, let's say this trajectory is geodesic equation, and we vary delta S, any way that the geodesic part is going to get zero, volumetric part will.
Yeah. So the point is, we didn't vary with respect to x because that we have already done.
Yeah, so we assume that it is going particle is on the geodesic. Any way that part will get.
You can say it this way if you vary with respect to all the variables, right? But the point, if you just look at the variation coefficient of delta G mu, right? There we have not so far used geodesic equation. Just the calculation of the coefficient of delta G mu. But you are right that if you have to vary with respect to every possible variable, right, then the geodesic equation is also part of it, right? That we have already said, right? So yes, so if you write the total variation as delta x times something plus delta G mu times something, then you have to separate the coefficient of delta x equal to 0 and delta G mu equal to 0. So delta x equal to 0 coefficient will give the geodesic equation, right? But it's just that while manipulating the coefficient of delta G mu, we have not used geodesic equation. Okay? That's all this is saying.
When we calculate equation of motion in general, in this case, if we write delta S as something delta G plus something delta X.
Yes.
These delta G and delta X should be
Arbitrary.
Should be independently
Vary. Exactly. Right? That's right. Yes, exactly. Right.
That's why we will get.
That's why the coefficient have to be 0.
And we are considering one of those equations.
Exactly. That's right. Yeah. In this case, we are just setting the delta G coefficient to 0. Right? Because delta X we have already done. Right? We only have to make sure that that equation you are not going to change. Right? And that means that whatever you are going to add should not depend on X. Right? Because if it did depend on X, then that equation will also get changed. Right? Because there will be delta X coming from here. Right? So we want this to be dependent. So whatever you are going to add, this S gravitational, we want it to depend only on the metric and not X. Is it clear? So let me write this again because I think it has gone below the board. So we need and you can more or less guess what the structure of the action should be except for the overall normalization. Because first of all, you see that the equation here has two derivatives, right? Each term has two derivatives because our Riemann tensor is constructed by taking two derivatives of the metric. So the action must also contain only two derivatives of the metric because this variation is not going to remove the number of derivatives. Right? You have delta J mu nu, there will be some derivatives acting on delta J mu nu, but ultimately you have to do integration of the parts to write it as delta J mu nu on something times something. So that number of derivatives are not going to change. So if you want an action if you want the equation of motion of this kind, then the action should be constructed out of two derivatives of the metric. Second, because the equation of motions are general coordinate invariant, right? We expect the action to also be general coordinate invariant. Okay, it's not strictly necessary. There are examples where you get covariant equations, but starting from non-covariant action. Okay? But let's just ignore that case here, right? So we assume that it will be general coordinate invariant. Right? So which basically leaves us with only one choice, that it will be integral of the scalar curvature, right? Because that's the only scalar that you can construct which has two derivatives, right? Other scalars like r mu nu rho sigma has four derivatives, right? Because r mu nu rho sigma has two derivatives, so you'll got altogether four derivatives in each term. So those are not, you can add those, but those are not going to give equations of this kind. Yeah, that suppose you start with an action which has two derivatives acting on different parts of G, right? Now you vary with respect to G, right? You replace G mu nu by G mu nu plus delta G mu nu. And what you are asking is how to extract the coefficient of delta G mu nu, because that's what we'll set to 0. Right? So in doing that, if there are derivatives acting on delta G mu nu itself, you have to do integration by parts and put the derivative on the rest, right? So delta G, it will be, so that it has a form delta G mu nu x times something. Right? So if you have two derivatives to begin with, right, then there may be terms where you have delta G mu nu and then both derivatives acting on other things of the metric. There may be terms where one derivative acting on delta G mu nu, the other one acted on the rest, right? But by the time you have integrated by parts, that derivative also acts on the rest. Yes. But it is square. So you have two time derivatives in the Lagrangian. It's dx dt square, right? So no vary, right? One ddt you integrate by parts and put it on the other one. Yeah, order of derivative is one. So you are not talking about order of derivative. We're counting how many total derivatives are there, right? Because Riemann tensor, for example, has terms which has square of single derivative terms, like gamma square, and then also two derivative terms, right? Yeah, so it's not order of derivative, it's no total number of derivatives that you have in the system. Is this clear? Okay. So basically then the S gravitational should be of the form integral d4x this is needed because d4x by itself is not general coordinate invariant, right? I think we had discussed it once. d4x, when you make an arbitrary general coordinate transformation, you get the Jacobian, right? X to x prime, there's a determinant del x prime that comes in, right? And that gets cancelled by the transformation of this, because determinant G is also not invariant under general coordinate transformation, and that Jacobian exactly cancels what you get from X transformation. So this combination is invariant. Okay. So you expect that S gravitational should be proportional to this.
Equation of motion had two derivatives. Right?
Yes.
And then actions should have how many derivatives?
Two derivatives. Yes. Each term in the action must contain net two derivatives, right? And this one does, right? R, right? You remember is R mu sigma G mu sigma, right? So this one is a sum of terms, but each of the terms have two derivatives, right? So when you contract to G mu sigma, this will be a sum of terms. Each will have two derivatives, right? And that's what we need, right?
When we take variation, when we take variation of R,
Yes.
there are already two derivative terms.
two derivatives acting on G, delta G.
Yeah, acting on delta G when we take by parts.
That those two derivatives act on G.
Yeah.
Right?
Okay. Yeah.
So at the end, after you have done integration by parts, right, the coefficient of delta G will have combination of G, right? Each of those terms will have two derivatives each, right? And that's exactly the structure that we have here. Right? Each of these terms have two derivatives. Two derivatives doesn't mean that second derivative, right? It could be either second derivative or square of a first derivative. Right? That's the way we are counting the number of derivatives. Yeah, Klein-Gordon, we have second derivative. Yeah, that's second derivative, right? But just like classical particle, dx dt square, right? That also has, we call it two derivatives, right? Even though it's square of a first derivative. Right? So the total number of derivative counting, you can do this without knowing the details of the form of the action. Is this clear? So I mean, this will also tell you that if for example you want to modify the Einstein's equation, right, by adding some extra term, right, say square of the Riemann tensor, right, and if you want to know is there an action from which I can derive that, okay? That will involve adding terms in the action which has four derivatives. Okay, so you can do derivative counting between equation of motion and the action in this way. Yes. Okay, what do you suggest? But the point is that dx mu means capital X, right? We don't want anything that involves capital X, right? Because that will change the geodesic equation, right? It has to be made only out of metric, right? Then out of the metric, the only scalar that you can get, right, which has two derivatives is R. Right? R mu rho sigma would have been okay, but that has four derivatives. Is this clear? Okay, so the answer, let me write. Is minus 1 over 16, sorry, plus 1 over 16 pi g. Okay. Plus total derivative terms, right, or boundary terms, which I will not write down. Okay, because when you take the variation, right, there will be some total derivative. We integrate by parts, right, and sometimes we may need to cancel those by adding some explicit boundary terms. Okay, so let me just briefly indicate how this proof goes, but I'll not go to the full detail. So delta of square root of minus determinant G is the first thing you have to calculate, right? Because it will be delta of S gravitational, it will be delta of this plus delta of this. Okay. So R I can also write as G rho sigma R rho sigma. Okay, I could have also written the other way, right? But there's a reason why I have written it this way. Okay, so this one we calculate by saying that this is half minus determinant G to the power minus half times delta of minus determinant G. Yes. Okay, because during this process you have to do various integration by parts, right? Okay. Integration by parts, sometimes you put boundary conditions so that the boundary terms are automatically zero, right? But for gravity, it turns out that the reasonable boundary conditions don't kill all the boundary terms. Right? So that's why you have to add explicit boundary terms to kill some of those. Right? You could have also put those boundary terms in the action. Right? Basically, the point is the following: that if you look at the integral root gr, right, and expand it out in say parts of the metric, right, there are terms which involve square of the first derivative of the metric, but there are also terms which involve second derivative of the metric. Right? So for second derivative of the metric, you have to do the integration by parts twice sometimes, right? Because suppose both derivatives act on delta G. Yeah, you have to do the integration by parts twice. And the first time you do the integration by parts, right, you get a boundary term that doesn't necessarily vanish by the boundary condition. Okay? And that you have to cancel by something else. No, it will not alter the equation of motion, right? Because boundary terms will just cancel the boundary terms, right? But the actual equation of motion will not be altered. So if you are willing to ignore the boundary terms, right? Say the boundary terms will be cancelled somehow. Then the actual equation of motion you can derive just from this.
This boundary terms we added to cancel the boundary terms coming from the
Yes.
So if I'm not adding this terms, then there will be terms which is coming from the derivative part.
That's right. Yeah.
Does that alter the equation of motion?
Well, that doesn't alter the equation of motion. I mean, there is nothing that you can do to equation of motion to cancel those terms. Yeah. It is say I agree that if you are only interested in getting equation of motion, right, there's no problem. Okay. But sometimes suppose you want to do quantum theory, you want to evaluate the actual action, right? Then the boundary terms could contribute. Right? You are trying to get a number, right? Suppose you do set of the Feynman path integral formulation, right? So in the semi-classical approximation, the leading contribution is just the value of the action. Right? There we have to sometimes take into account the boundary terms. Right? But if you're only interested in getting equation of motion, then I agree that there's no problem. You can just forget about the boundary terms. Yeah, the G vanishes sufficiently fast at infinity. Well, derivative also you put some condition, but what turns out is that those conditions are not good enough, not strong enough to make the boundary terms vanish. Right? That's why you needed the boundary term. Right? It's a question of whether the fall off is sufficiently fast so that all the boundary terms are zero. Right? But the kind of interesting solutions that you are looking for, right? It turns out that the fall off is not sufficiently fast. Right? And that's why I need this boundary term to cancel those. Okay, but at the end, if you are only interested in the equation of motion, right, without caring about the value of the action, then you can say, okay, there are some boundary terms which cancel this, but you don't care. Is this point clear? Okay, so this one, there is a general result, right, which are not proved, but this is that's a question of matrix identity, right? That if you take a determinant of a matrix and vary the matrix, right, what do you get? So this is basically minus determinant G times G rho sigma delta G rho sigma. Okay, this I'll leave as an exercise. This is just a matrix identity, right? The variation of the determinant of a matrix, right, is the determinant of the matrix times G rho sigma times delta G rho sigma. This is just matrix manipulation. Is this clear? So then this term, we see that, so this net term then is half minus determinant G to the half, because it's minus half and minus determinant G combined into minus determinant G to the half times G rho sigma delta G rho sigma. So you see that when you vary this, right, we get 1 over 16 pi g, okay, times half g rho sigma delta g rho sigma. That's exactly one of the terms you want. Okay? 1 over 16, this minus and minus gives you plus, right? 1 over 16 pi g times half delta g mu nu. Yeah, so g mu nu delta g mu nu, right? That's exactly what we have here. Right? The sign is correct. You need plus half. Right? Minus half and then this minus sign. Is this clear? Then we have this term, the variation of this. Right? So another term is so minus square root of determinant g, okay, delta g rho sigma r rho sigma. We have to write it in terms of delta g with lower components, right? Because the equation of motion here has delta g with lower components. So g upper rho sigma is just the rho sigma component of the inverse matrix, right? And we use the fact, we use the identity, the delta of M inverse is minus M inverse delta M inverse. If you vary the inverse a matrix, right, its inverse varies by this. Is this familiar? Okay, it just follows from this fact that delta of M inverse M is delta of identity, which is 0, right? So delta M inverse times M plus M inverse delta M equal to 0. Right? So you can take it to the right hand side and then multiply by M inverse from the right. So that gives you delta of M inverse is minus M inverse delta. So this then can be written as minus determinant g, g rho tau, g rho mu, delta g mu nu, g mu sigma r rho sigma, and that's nothing but square root of minus determinant g delta g mu nu r mu nu. Gets you the minus sign. Thank you. So when you vary this delta g rho sigma, right, you recover minus 1 over 16 pi g times delta g mu nu r mu nu. Right? That's exactly this term. Minus 1 over 16 pi g delta g mu nu r mu nu. Right? So two of the terms you have gotten. Right? In fact, all the terms you have gotten, right? So whatever is left better be 0. So the final variation will be this one, right? R has to be varied. Right? This one you have not varied. So integral, so 1 over 16 pi g, integral square root of minus determinant g, delta g rho sigma, delta r rho sigma. Sorry, g rho sigma. Thank you. Okay. This one is a little more complicated to analyze, right? Because you have to use the fact that we have to write R in terms of Riemann tensor, right? This is basically delta of R mu rho mu sigma. That's the definition of the Ricci tensor, right? So you have to express this in terms of the derivatives of the metric, right? It's first express this in terms of the gammas and then derivatives of the metric. Okay. But the net result that one finds is that this is a total derivative. This becomes integral of total derivative. And hence it's 0 up to boundary terms. It is 0 up to boundary terms. So these I'll leave as an exercise to check. Okay, it's straightforward, but it involves some algebra that you have to do. Yes, you have to include boundary terms that will cancel these, right? Some of the boundary terms will go away by the boundary condition, right? But not everything goes away, so you have to include the boundary terms that cancels this. Is this clear? Okay, so then this is the action. This plus this, sorry, is gravitational, I wrote somewhere here. This one plus Sx when you vary, right? The variation with respect to x gives you the equation, geodesic equation for x, and the variation with respect to g mu nu gives you the equation for g mu nu, the Einstein's equation. Is this clear? So then you just have to write one action instead of writing many equations, right? Given one action that contains all the equations, right? Both the Einstein's equation as well as the geodesic equation. Yes, that you should get the Einstein's equation, right?
I'm just saying, take one way to calculate the energy momentum tensor is take the variation.
Yes, indeed, exactly. Yeah. So if you take the action, right, forget about the gravitational part, right, and vary with respect to the metric, then that gives you energy momentum tensor, right, or half of the energy momentum tensor. Okay, that's what we found from this explicit analysis, but this is general feature, right? In fact, often that is used as a definition of the energy momentum tensor, right? If you define the energy momentum tensor as whatever appears on the right hand side of Einstein's equation, then that's the definition, right? You vary with respect to the metric and you should get the energy momentum tensor. Okay? But then of course it's a question that you have to make sure that it's the same as the other ways of defining energy momentum tensor that you will be familiar with. Yes. Yeah, Noether procedure doesn't always give you symmetric energy momentum tensor, and you have to do some work to make it symmetric. Okay? This procedure always gives the symmetric energy momentum tensor. It better do, right? Yeah. So in the cases that are known, it does match with this procedure. Yeah, you add something whose integral gives you 0, right? So it doesn't change the definition of energy or momentum, right? But the currents it changes. The Noether procedure really tells you the conserved charges, right? The integrals, right? And from there you extract what the currents are. But in extracting the currents, right, you can add total derivatives, right, which integrate to 0, and by adding those, you can make the energy momentum tensor symmetric. Right? But what we see from here is that for coupling to gravity, is essential that you use the symmetric energy momentum tensor, because if you define, if T mu nu has to be the variation with respect to G mu nu, right, it better be symmetric. Any other question? Okay, so now I'm going to generalize this to include electromagnetism. So flat space Maxwell action. Are you familiar with the flat space Maxwell action? Right? What Maxwell's equation you know in the covariant form, right? What action do you have to vary to get the Maxwell equations, right? So the flat space Maxwell action is basically minus 1/4 integral d4x. So if you vary, yes, F mu, let me remind you, if you vary, yes, you will get 4 identical terms because you can vary this or this, which is gives us the same result. Right? And inside F mu nu, you can either vary the nu here or mu here, right? Which are also gives the same because of the antisymmetry of the other one. So you can just vary one and multiply by 4. Integral d4x. So here I write is this clear what I have done? Right? Just 4 variations, right? Because you can either vary from here or here, and each of these have 2 because there are 2 terms. Right? You can vary the first one or the second one. Right? All of them give the same answer, so I've just varied the first one of the first term. That's this one. So this is you can integrate by parts. That's basically right. So if you say delta, so delta SEM equal to 0 will give you is the flat space Maxwell equation. Free Maxwell equation. Flat space Maxwell equation in absence of source. Yes.
Del mu, so it's a boundary term. It's like delta nu at the boundary.
Yes.
Right. So why we do the similar in the
Yeah. So delta G mu nu may be 0, but delta of derivative of delta G mu nu may not be 0.
that we can't put that condition.
Yeah, you cannot put both conditions, right?
Why can't we do that?
Because that's too restrictive. I mean, if you try to do this same thing here, for example, right? I mean, you should be able to have very independently, right? That either you put the derivative of delta a equal to 0 or delta a equal to 0, right? But not both conditions. Right? That's how the variational principle works, right? That you fix the a at the boundary, right? And then you vary.
Here we are not running into problem that we have both variation of the metric and variation of the field and variation of the derivative.
Yes.
Here this is not happening.
It's not happening, no. And the reason that it's not happening is because each term has only one derivative, right? You could have written it in a way where that will happen, right? And that will cancel. That will have to be cancelled over the boundary term. Let me explain this. That suppose you could have written this electromagnetic action as integral d4x right? Just do some integration by parts, right? You write this in this form, right? Then symmetrization means that you can just drop this, multiply by a factor of 2, and there's a half here. You don't get rid of the 1/4, but half, because only one term you are this factor you are removing, right? That gives a factor of 2, and then this we just integrate by parts and put it there. Okay. Notice that in that process you would have gotten some boundary terms which I have not written, right? But let's now see without those boundary terms what happens. Right? Now you vary nu, right? One term will be delta nu times this. No problem with that, right? But the another term where it will be nu times the variation of nu from here, right? That's so two derivatives acting on delta n. So now you have to integrate by parts to move those two derivatives on the other side, right? The first time you integrate by parts, right? The boundary term that you get is a derivative of delta n, right? That you cannot ignore, right? Because you have said delta nu equal to 0 at the boundary, derivative of delta nu is not 0. Is that right? So even though this equation and that equation, this action and that action looks like they are related by integration by parts, they differ by a boundary term. Right? So if you want to use this term, this action, right, you have to add a boundary term. Okay, this boundary term is exactly what we have ignored in going from here to there. Yes, you can. It won't be covariant, right? Exactly. So that's the problem. Right? You can expand the Einstein's action in components, right? There will be gammas and gamma square and derivatives of gammas, right? Whenever you have derivative of gamma, you just integrate by parts to put the derivative on the other side, right? So that no factor of metric contains two derivatives. Okay? The only problem with this is it will not look covariant. Manifestly covariant, exactly. Right? It will not look manifestly covariant. Yeah? So if you want to write it in a manifestly covariant form, right, then you have to add the boundary term. Right? Electromagnetism didn't have that problem, right? In fact, this is not manifestly covariant, right? This is manifestly covariant. Because it's a conflict between writing things in a manifestly covariant form, right, and avoiding two derivatives acting on a field. Under gauge transformation, exactly. Yeah, I should have said manifestly gauge. It's not manifestly gauge invariant, right? Because there is nu sitting there. Exactly. So role of gauge invariance is played by general coordinate invariance, but the situation is reversed. Here, this form is not manifestly gauge invariant, right? And you have to add boundary term. This one is manifestly gauge invariant, and you don't need any boundary term. It's the opposite, right? They are the manifestly covariant form requires boundary term, right? Because manifestly covariant form has two derivatives acting on the matrix, right? And the non-covariant form, right, doesn't require boundary term. So this is basically the difference between the way Einstein's action is written and Maxwell's action is written. Right? But you could have written the Einstein's action in the single derivative form, right? The square of single derivative by doing some integration by parts, right? It's just not manifestly covariant. Is this clear? Okay, so this gives you the Maxwell action in absence of source. Okay? But let's also ask what happens in the presence of source. Okay? So the Maxwell action in presence of source. That is given by okay, where J mu is a current. Is this familiar? Maxwell action in the presence of source, right? If you now vary with respect to nu, right? So the equation of motion that you get you will have, where did I get? Yeah. You will have this term. Right? Because delta nu coefficient, we can make this nu if you want. Delta nu coefficient will not have extra term which is nu. Is it okay? But this serves another purpose, this term. Okay, that's the advantage of action principle. This will also tell us, right, the same term in the action will also tell us how the equation of motion of x changes. Of x, right? Imagine that you have a charged particle, right? You remember the expression for J mu for the charged particle. That's integral du E remember this, right? So if you substitute this here, we get basically the x integral can be done with respect with the help of the delta function. Okay. And you get E integral a mu of x of u du is there. Is it okay? So if you substitute for J mu, the source due to a charge particle, you get this term in the action. This term now has X dependence. Right? Remember that we had written down the relativistic point particle action, right? Where with respect to X to get a geodesic equation, right? In flat space, right? That's just d2x mu d tau square equal to 0. But now it's going to change, right? You have to vary this also. Is that clear? So let me describe what this is. So delta of integral a mu of x this will be given by integral du. First, delta a mu of x, right? Because why does delta a mu of x vary? You are trying to vary x, right? But the argument varies, right? So the first variation will be let me write this delta of x, right? So that it's clear that you are only varying x, right? Because Maxwell's equation you have already got by varying with respect to a mu, right? Now we are asking what happens when you vary with respect to x. Is clear? Right? You are varying the argument, right? So you get this plus integral du a mu of x of u d du of delta x mu. This one you have to integrate by parts, right? Because you have to free delta x mu to get the equation, right? Contribution to the equation. So you have to integrate by parts. So I write this as the integral d mu du minus integral du. Okay. So d du now acts on this. Right? Again, it acts on this because x depends on you. Okay. So this gives you we have to exchange the indices. Let's try to do that. So sigma, we want to make first of all the sigma into a mu, right? Because sigma into a rho. We want to make the sigma into a rho, right? Because there is a delta x. Sorry, what did I want? We want to make rho into
Sigma a rho. Yeah, I mean, but replace sigma with rho because it's anyways dummy.
yeah, but the main point is we want to make this into rho, right? So let's put this into this as rho first, right? Then there's no confusion. Okay, then I can replace sigma by mu, right? So that is sigma by mu. So now you see that we have the combination d rho a mu minus d mu a rho, right? So that's integral du f rho mu So exercise, check that together with delta Sx. Sx is the original action that I started with, the first action that we wrote down today, right? This gives a Lorentz force law. Is it clear? Okay, so next let me just write down the now coupling to gravity and then I'll be done. So Sx we have already written earlier, right? So we have to write the action for electromagnetism and the coupling of electromagnetism to X. This we didn't take into account earlier, right? The X we have already written, that first action that we started with. So this one, the generalization is straightforward. We basically have to covariantize everything. F below. Plus, this one I can write in different ways. D4x square root of minus determinant g of x. This one we had defined earlier. If you remember, J mu, covariant form of J mu we had defined, right? That's what you have to substitute. You can also write this in an exercise to check that this combination, once you put the covariant form of J mu, this also becomes integral du E integral du basically this square root of minus determinant g that you see here gets cancelled against the 1 over square root of minus determinant g that is they are in the definition of J mu. And if you go back to your notes, you'll find that there is 1 over square root of minus determinant g there, and they all cancel, and eventually you get this. So exercise 1. That we get covariant form of Maxwell equation and Lorentz equation. Okay, covariant now means in the presence of background metric. Okay, so what is the covariant form? D mu F mu nu equal to minus J mu. Right, where all these are raised and lowered now by the metric. Right, this is the covariant form of Maxwell's equation. Right, similarly, Lorentz force law also we wrote down a covariant form. Okay, and Einstein's equation, and so this is the second exercise. Einstein's equation with Ex plus TEM or RHS. TEM comes because this one now has non-trivial dependence on the metric. Right? Metric enters everywhere. So you have to vary with respect to metric. Right? That is going to produce the electromagnetic energy bond potential. Fortunately, in this form, there's no metric over here. So this doesn't give any extra contribution to the energy bond potential. This is very special to electromagnetic kind of interaction. Right? In general, if you add some interaction in the action, okay, that will require metric to make it covariant. And once it requires metric to make it covariant, it will also contribute to the energy momentum tensor. Right? So everything contributes to the energy momentum tensor, right? Even interaction energies. Because if you have to write the interaction energy in terms of the metric, you have to vary with respect to the metric. Right? So from that perspective, this electromagnetic kind of interaction is very special because it doesn't depend on the metric. Right? You can say you can write it in a way which has no knowledge of the metric, and hence it doesn't contribute to the energy momentum tensor. Okay, I think I'll stop here. Are there questions? Exactly. In general, there will be third term. Right? So when you have, for example, if you take a field theory, right, of say two fields, right, phi and psi, and if there is an interaction term that involves phi with psi, right, that interaction term will also contribute to the energy momentum tensor.
Suppose now we don't take gravity dynamics. That should also appear when you do the Noether procedure for that interaction.
Yes, it should. Yeah. So in this case, if you do Noether procedure, right, this term doesn't affect the energy momentum tensor. But Noether procedure always has this feature that you may not get a symmetric energy momentum tensor, right? You have to do make some special effort to make it symmetric. Yeah, you have to add some antisymmetric part whose integral gives you 0, right? See, because I mean you cannot add any arbitrary antisymmetric part, right? It has to be conserved and its integral should give you 0. Right? That's the way you symmetrize energy momentum tensor in Noether procedure. But if you use gravity, it is automatic, right? You just couple the action to gravity, vary with respect to g mu nu, and you automatically get a symmetric energy momentum tensor. Because g mu nu is symmetric, exactly. Well, I mean here, this argument is more than just that, right? The fact that you can couple it to a metric, right? The general coordinate invariant.
So is there a relation between the what happens is first
yeah, there is a relation because after all you have to have a Lorentz invariant theory before you can couple it to general, right? To covariantize, right, the minimal coupling prescription, you need a Lorentz invariant theory to begin with. Exactly, yeah. Right? Because that's the way you generalize your equation of motion, right? Okay, so we'll continue next time. So tomorrow there is no class, so the next class will be on Thursday. And I think next week, one of the classes will be a tutorial. So we'll let you know when. Yes.
The diagram that we drew last time for the Swastika solution.
Yes.
So in that, for the constant row slices, so if we want to remain on a constant row slices, as we go, as the time increases, we'll have to keep on accelerating, right?
Yes.
The rate of acceleration itself will increase. Because if we look at the tangent, the slope.
Yeah, but see, in this diagram, the tangent by itself is not a reflection of the acceleration, right? You have to convert it to local inertial frame, right? In the local inertial frame, you will find that the acceleration is constant.
Oh, okay.
Because, I mean, you can also see it just from time transition invariance, right? Because if you are sitting at a fixed point rho, the geometry is not changing, right? So you expect that you should have to apply the same acceleration to remain there. Okay? Yeah, so that diagram is a little misleading because of this fact that you have to go to the local inertial frame. Yeah. Thank you.